Hello, good morning. I am Dr. R.V. Parimala, working as professor at BNMIT, Bangalore. I am going to discuss today about the second module of electric circuit analysis. The topics to be covered under this are analysis of networks with and without dependent AC and DC sources by Thevenin's and Norton's theorems, analysis of AC and DC circuits for maximum power transfer to resistive and complex loads, application of Millman's theorem to multi-source networks, application of superposition theorem to multi-source networks, reciprocity theorem and its application. Before we start concentrating on any particular theorem, these are the important things we need to understand. The first thing is linear and non-linear circuit elements. We basically need to know what is a linear element and what is a non-linear element and where exactly we are going to use it, and with the help of these elements, what are the things we are going to analyze. Linear and non-linear elements generally which exhibits the linear characteristics between voltage and the current. So the current varies linearly with the variation of voltage. So if the current varies linearly with the variation of voltage, then the elements are called linear elements. We already have come across the elements such as resistor, inductor and the capacitor. If you just observe the relation between the voltage and current of all these elements, we will come to know that there exists a linear relationship between the voltage and current in case of all the three elements over here. So the element resistor, where we have V is equal to I into R. Similarly, for L and C, we have the linear relationships, and the graph there exhibits the linear characteristics. You can just observe here, as the voltage varies or the current varies, the other parameter is also going to vary linearly. That's why we have a ramp kind of variation which we can observe here. So if you find any element exhibiting such characteristics, then we called such elements as linear elements. Then what are non-linear elements? The non-linear elements are those whose current does not change linearly with the change in applied voltage. Examples are diode, transistor, light dependent resistor, etc. So if you come to the case of a diode, you have seen that it has only the forward bias mode, and in the reverse bias mode it is open circuit. So we say that similarly even in case of transistor and light dependent resistor. So these elements are called non-linear elements. Then coming to the second important parameter, or second important characteristics which we need to know is what is a unilateral and bilateral elements. If the VI characteristics remain same in both first and third quadrant for an element, then such elements are called as bilateral elements. Once again, the example for such the unilateral, once again the example for bilateral elements are resistor, inductor and capacitor. If the voltage current characteristics differs in first and third quadrant for an element, then such an elements are called unilateral elements. Examples are diode and transistor. As I have told, for the forward bias mode, the behavior of diode and transistors are different, and for the reverse bias mode, the behavior of these elements are different. Then we have lumped and distributed elements. A network in which all the elements are physically separable is known as lumped network. So all these elements which we can physically separate it and make the connections again, then such elements are called lumped elements. Most of the electric network consisting of elements of R, L and C are lumped in nature, whereas networks in which the circuit elements like R, L and C cannot be physically separable for the analysis purpose is called distributed network. So what exactly we mean by that? If you take the example of transmission system, we will be having only the transmission lines. You can observe even outside your houses, the transmission lines running. So transmission line, if you observe, you cannot see any physically existing resistor, inductor or the capacitor. But we have as such the resistor, inductor and capacitor throughout the length of this particular line, even the distribution network or the transmission network. Transmission lines are the distribution networks. You have the resistor, inductor and capacitor distributed over the length. So what exactly we mean by that? What is actually that? Any line exhibit the characteristics of resistor. It has the elements such as resistor and inductor over there. Then coming to the point of capacitor, since the transmission lines are carrying the voltage there, the lines, between the lines, each is a conductor, and between these two conductors, both of them are charged, and hence we actually found a virtual capacitor between the two lines. Between the two lines, since both of them are charged, we say that there exists the property of the capacitance over there. Similarly, from any one line to the ground, from a line to the ground also we say that it is the capacitance which exists, because the line is charged whereas the ground is at zero potential. Similarly, between the any two lines, both the lines are charged. It's like two charged conductors. The two charged conductors which is separated by a dielectric is nothing but the capacitor, and hence we say that it is the capacitor over there. So distributed elements that we are going to come across in case of transmission and the distribution network, whereas the lumped parameters or the lumped elements are those elements which can be physically separable and make the connections as such. The fourth one is active elements, and the final one is a passive elements. Active elements are those which possess energy of their own and impart it to other part of the circuit, or they have the energy of their own and they supply that energy to the other part of the circuit. Such elements are called the active elements. So the examples are voltage sources, current sources, transistors, diodes, operational amplifier, etc. These are the active elements. Then coming to the passive elements, which do not have the energy of their own. They cannot possess the energy of their own, and they need energy from the external sources such as voltage source or the current source, are the passive elements. The best example once again for the passive elements are resistor, inductor and the capacitor. So with these prerequisites, with having all this knowledge, that is knowing about the active network or the active elements, and also linear network and the bilateral network, we will start talking about or discussing about the different theorems that we are going to come across. The first important theorem that we are going to discuss today here is Thevenin's theorem. So before we start discussing about Thevenin's theorem, let us also talk about independent sources and the dependent sources, because these are the important things to be known, so that the application of these sources or inclusion of these sources in the network, how it is going to affect rest of the circuit, and how to use these independent sources and the dependent sources to write the equations by applying Kirchhoff's voltage law or Kirchhoff's current law are the important factors to be discussed here. What are the independent sources? So independent sources, they produce the energy of their own. They produce the energy of their own, and they are not dependent on any other sources or any other part of the circuit as such. So they are called the independent sources. And again, under independent sources, we have two classifications: one ideal and the actual or practical. Again, ideal and practical sources are classified into the voltage sources and the current sources. So ideal voltage source can be represented by this, where in case of ideal voltage source, there won't be any resistance in series with it, which we call it as internal resistance, or if the internal resistance is absent, then it is called ideal voltage source. Then coming to the practical voltage source, it has an internal resistance in series with it for a DC circuit or for a DC battery. In case of AC, we call it as the impedance here. So you have a source and an impedance or resistance in series with it is for the practical voltage source. This is the representation of practical voltage source. Then coming to the ideal current source is without any internal impedance or the resistance across it. So the representation of ideal current source is this. Then coming to the practical current source, it has a practical current source will be having a resistance or an impedance across it. It will be connected between the two terminals of the current source. Then it is called practical current source. Then we have the dependent source. So dependent source, the output of such sources are dependent on certain parameters, maybe voltage or current. Depending upon which particular parameter it is dependent on, it is once again classified as voltage controlled and the current controlled. So voltage controlled voltage source or current controlled voltage source or current source. That's what we are going to have it here. For the voltage controlled voltage source, the representation is generally with a diamond shape with plus and minus sign represented over there, and you can just observe here it is 3Vx. So the magnitude of the voltage of this particular source is dependent on Vx, where Vx may be the voltage across certain part of the circuit, across a resistor, maybe across an inductor, or maybe across the capacitor, or maybe some impedance. Okay, so it is 3Vx. 3Vx represent that it is the magnitude of the voltage 3 into Vx. Vx is the voltage across any part of the circuit. Similarly, we have voltage controlled current source. It's a current source. Always a current source is represented by an arrow mark, and arrow mark indicates arrow mark indicates the positive direction of the current flow over there. Here we can observe it is 5Vy. That means the output of this current source is dependent on Vy, which is a voltage across certain part of the circuit. Next, current controlled voltage source. Again, we have the same example here, 5 into Ix. Ix is the current flowing through certain part of the circuit, maybe through a resistor, inductor or capacitor, or maybe through some part of the circuit. So similarly, we have current controlled current source. Current controlled current source, once again the symbol is like this. It is 10 Iy. Iy is the current that is flowing through certain part of the circuit. Next, Thevenin's theorem. We need to discuss about the different theorems that we are going to come across in this particular module. The first important theorem that we need to discuss here is Thevenin's theorem. For understanding, the proper understanding of any of the theorems, whatever we have discussed just now as prerequisite is very important. So knowing all those parameters, we can start concentrating on the different theorems that we are going to come across in this unit. So what is the main objective of Thevenin's theorem? Why we need to study Thevenin's theorem? Already you have discussed about Kirchhoff's current law, Kirchhoff's voltage law, application of Kirchhoff's voltage law and current law to the circuits, and you have already done different type of analysis over there, that is mesh analysis, node analysis, super mesh analysis, super node analysis, everything you have done, and you have found out the current through a part of the circuit and the voltage across it, or the power dissipated in a part of a circuit, everything you have discussed with KVL and KCL. Then what is the need of Thevenin's theorem? So basically Thevenin's theorem is to simplify our calculations. So in order to simplify the laborious work, we go for Thevenin's theorem. What is actually that? The main objective of Thevenin's theorem is to reduce some part of a circuit to a single equivalent voltage source in series with a single resistance or impedance. This reduced equivalent circuit connected to the remaining part of the circuit will allow us to find the desired current or voltage. Most of the time, we may have to find out the current through a particular resistor, the voltage across a particular resistor or impedance, or maybe the power dissipated in a part of the circuit. In such cases, we have to reduce the rest of the circuit to a single voltage source in series with a single resistance in case of a DC circuit, or single voltage source in series with a single impedance in case of AC circuit. And then when you reduce that circuit to a single voltage source in series with a single impedance, then connecting the other part of the circuit may be a single impedance or a single resistance, makes a single loop over there, and just by applying Ohm's law you can find out the current through that, or you can find the voltage across it, the power, etc. So that's a main objective. So Thevenin's theorem basically used here, or we are going to study here to simplify our calculations. So what is it then? According to Thevenin's theorem, the linear circuit of the figure 1a, whatever of this particular figure, can be replaced by a circuit shown in the second figure. The load may be here, in the first figure may be a resistor, or may be an impedance, or may be another circuit. Okay, it need not be a single resistor or impedance, it can be another circuit also. The circuit to the left of the terminals in this figure, see whatever we have here, a source and a resistor, you can observe here, this is called Thevenin's equivalent circuit. Next, so once we know the objective and how exactly we are going to get it, then we go for the statement of Thevenin's theorem. The statement of Thevenin's theorem is very important. We need to know the statement very clearly here. We need to understand the statement clearly. So once we understand the theorem clearly, then we can apply the theorem to the different circuits and simplify the circuits. So what exactly is statement of Thevenin's theorem? Any two-terminal linear active bilateral network can be replaced by an equivalent circuit consisting of a voltage source V Thevenin in series with a resistor R Thevenin. So V Thevenin is common even for AC circuit or DC circuit. That's why here in the bracket I have written R impedance. So the same statement we can use both for AC and DC circuits. In case of DC circuit, we say that any two-terminal linear active bilateral network can be replaced by an equivalent circuit consisting of a voltage source in series with a resistor. Whereas in case of an AC circuit, we say that this can be replaced by a single circuit consisting of a voltage source in series with an impedance, where V Thevenin is the open circuit voltage at the terminals and R Thevenin, or the impedance at Thevenin, is the equivalent resistance or impedance measured between the terminals of the network with all the independent sources replaced by its internal resistances or impedances. I repeat, where V Thevenin is the open circuit voltage at the terminals and R Thevenin or Z Thevenin is equivalent resistance measured between the terminals of the network, or we say that the output terminals are looking into the circuit from the output terminals. We have to find out the equivalent resistance by replacing all the voltage sources by its short circuit if it doesn't have any internal impedance or resistance. If internal resistance or impedance is present, then replace the voltage sources by its internal impedance or internal resistance, and current sources, ideal current sources, by an open circuit, or the actual or the practical current sources by its internal impedances again. Next, coming to the explanation part of it. So let us consider the circuit shown here. If it is required for us to find the current through the load resistance RL, this circuit is a two-loop circuit. Easily we can solve this by applying KVL also. Just for understanding purpose, I have taken a simple circuit here. Just to understand how exactly we can apply Thevenin's theorem to solve for current through a load circuit, or the voltage across the load circuit, or power dissipated in the load circuit. So for that purpose, I have taken a very simple circuit here. So now this circuit is consisting of a voltage source V, resistor R1, R2 and R3. Voltage source V, R1 and R2 forms one loop, R2, R3 and RL forms the other loop here. Okay. So in this case, for this circuit, if we have to find out the current through the load resistance RL by applying Thevenin's theorem, what are the steps to be followed? The first important step is to remove the load resistance from the circuit. Okay, as soon as it is asked to find out the current through a load resistance by applying Thevenin's theorem, the immediate step to be followed is to remove that resistance from the circuit. So that is, remove the resistance from the circuit. So as soon as we remove the resistance from the circuit, an open circuit will be created here. There won't be any connection between A and B. So it's an open circuit. So next step is to find out the voltage across the terminals A and B. In order to find the voltage across the terminals A and B, what is it equal to? We have to analyze how to find out the voltage across A and B. So generally speaking, the drop across the resistance R2 and the drop across the resistance R3, if it is there, the sum of these two should be the voltage across AB. But R3, if you just look at it, it's an open circuit. Since it's in the open circuit, no current flows through R3. Since no current flows through R3, the drop across the resistance R3 will be equal to 0, because the voltage drop across the resistance R3 is nothing but equal to the current flowing through that multiplied with the resistance R3. Since current is 0 for an open circuit, I into R3 part is going to become 0. So if that is 0, in that case, the voltage across the terminals AB is nothing but equal to the voltage across the resistance R2. Okay. So if we have to find out the voltage across the resistance R2, then it's a single loop circuit. Just by applying Ohm's law, you can find out the current through the circuit. So the current through the circuit is nothing but equal to V divided by sum of the resistances R1 plus R2. So this part V into R1, V divided by R1 plus R2 is nothing but the current flowing through the circuit. That is current flowing through the first loop. So this current is flowing in the downward direction. Since it is flowing in the downward direction, and we also know that current flows from higher potential to lower potential. So the uppermost point is positive here and the lowermost point is negative. So this A, so considering the same concept here, uppermost point corresponds to point A. So A is positive and B is negative. So now find out, after finding the current through the current, the next step is to find out the voltage across it. The voltage across it is nothing but equal to the current multiplied with this resistance, I into R2. So where I is equal to V divided by R1 plus R2 into R2. So this gives you the voltage across AB. Voltage across AB, as we have seen, it is an open circuit voltage, or this is also called Thevenin's equivalent voltage, V Thevenin. This is how we have to find out Thevenin's equivalent voltage. The steps to be followed are: remove the resistance from the circuit, create an open circuit over there, then find out the voltage across the terminals AB. So which is nothing but equal to V Thevenin. What is the next step? Next step is to find out Thevenin's equivalent resistance for the circuit. In order to find out the Thevenin's equivalent circuit, Thevenin equivalent resistance for the circuit, as already mentioned, you have to replace the voltage source which was there in the earlier circuit, that is V, you have to replace it by its internal resistance, or if internal resistance is present, otherwise by a short. That's what we have done here. It doesn't have an internal resistance, so it is shorted here. Okay. So now we have to find out the equivalent resistance by looking into the circuit from output terminals, or measure the resistance from the terminals AB. So arrow mark shows that instead of finding the resistance from left to right, the resistance calculation left to right, do it from right to left. What does it mean? That means, assume that we are sending a current at this junction, that is through R3. If I send a current at this junction, you can just observe two paths, one through R1, the other through R2. So if one is through R1, the other one is through R2, it means the two resistors are connected in parallel. We know that current divides in case of a parallel circuit, and the same current flows through a series circuit. So as soon as I send a current through R3, at this junction it finds two paths and it divides between these two paths. That means R1 and R2 are in parallel, okay, together, that is in series with R3. So that is R Thevenin. So looking into the circuit from output terminals, if you try to find out the equivalent resistance, it is R3 in series with the parallel combination of R1 and R2. Okay, so that's why the expression here R3 plus R1 in parallel with R2. So if you know the relation for the parallel combination of two resistors, it is R1 R2 divided by R1 plus R2. So that R Thevenin for the given simple circuit is R3 plus R1 R2 divided by R1 plus R2. So we have got Thevenin's equivalent voltage and Thevenin's equivalent resistance. The next step is to replace the existing circuit by Thevenin's equivalent circuit. So Thevenin's equivalent circuit, as I have marked here, is a single voltage source in series with a single resistance. Okay, the single voltage source is V Thevenin and the single resistance is R Thevenin. So this part of the circuit is representing Thevenin's equivalent circuit. You can just observe only one source in series with a resistance here. To this series combination, connect the load resistance through which the current is to be calculated. So after connecting it, you just find that there is only one single loop. So you can find out the equivalent resistance, which is nothing but equal to the series combination of RL and R Thevenin. So the equivalent resistance is RL plus R Thevenin, and you have only one voltage source, which is V Thevenin. Just by applying Ohm's law, you can find out the load current IL, which is equal to V Thevenin divided by R Thevenin plus RL. This is the way how we can calculate the current through any resistor by applying Thevenin's theorem. This is the simple example which I have taken. Next, in case if we come across a different type of sources, I just now took independent source. If a dependent source is there, in that case, how to solve the problem by applying Thevenin's theorem, how to find out Thevenin's equivalent voltage, how to find Thevenin's equivalent resistance or the impedance. So those are the questions which arises in anybody's mind. So for that case, we are discussing three different types of circuits that we are going to come across while determining the equivalent resistance or Thevenin's equivalent resistance by applying Thevenin's theorem. So what are the three different types? The first one, as I have already discussed, the circuit contains only independent sources, the one which I have discussed right now, and resistors. Deactivate the sources and find by circuit reduction technique. Deactivate the sources means you reduce the voltage to 0 or replace it by a short circuit if it is an ideal source, or replace it by its internal resistance. Independent current sources are deactivated by opening them, while independent voltage sources are deactivated by shorting them. The same thing I have just now told. Next, that's the one which we have already discussed in a previous example. Next, if the circuit contains resistors, dependent and independent sources, both dependent and independent sources if exist, then follow the instructions given below. What are the instructions we have to do? Determine the open circuit voltage VOC or V Thevenin with the sources activated. That means having the sources in the network, find out the open circuit voltage, or which we call it as the Thevenin's equivalent voltage, by using the same method whatever we have done. So in case if we have to find out the current or the voltage through any element, and in that circuit if we have both dependent and independent sources, in such cases you have to open the load resistance and then you have to find out the open circuit voltage or the Thevenin's equivalent voltage at the open circuited terminals. Next, short the open circuited terminals and find out the current through that terminal, which we call it as short circuit current. So find the short circuit current when a short circuit is applied to the terminals. So initially we open circuit it to find out the open circuit voltage, and then only short it, do not connect any resistor or impedance there. So just by shorting it, find out the current through that short, and that current is called short circuit current. You have open circuit voltage VOC or Thevenin, and you have the short circuit current. So knowing the voltage and current, by applying Ohm's law, you can find out the resistance or the impedance, which we call here as R Thevenin equal to VOC by ISC. So if the circuit contains resistors and only the dependent sources, so if you have only dependent source, we have already discussed about the dependent source. Dependent source is dependent on the voltage or current in any part of the circuit, in some part of the circuit. And if the independent source is absent, then such circuit is called passive circuit. Even though you have a dependent source, that cannot be an active network. So you have only the dependent source. In that case, you cannot find the open circuit voltage or the Thevenin's equivalent voltage. Dependent source is a passive element if an independent source is absent in the network. Okay. So in that case, if the circuit contains only the resistor and the dependent source, we cannot calculate or we cannot find out open circuit voltage or Thevenin's equivalent voltage. So VOC will be equal to 0, or Thevenin is equal to 0. That's why, since there is no energy source, there should be an energy source for the dependent source to act. So if that is absent, then your open circuit voltage is also equal to 0. Then to find out equivalent impedance, that is possible because it's a passive network, resistance or the impedance is existed, then you can find out equivalent impedance there, but not the voltage. So in order to find out that, we need to have one energy source. So just assume that we are connecting a 1 ampere current source to the terminals AB and determine VAB. What are the terminals AB? That is the output terminals, and there you connect 1 ampere source and try to find out VAB, what it is equal to between those two terminals, and find out R Thevenin, which is equal to VAB by 1, where 1 is the current and VAB is the voltage which we have calculated. These are the three methods by how we can find out the equivalent impedance, that is Thevenin's equivalent impedance. The corollary of Thevenin's theorem is nothing but equal to the Norton's theorem. So it is like the source transformation. In case of source transformation, you people have studied about voltage source to current source and current source to voltage source transformation. So Thevenin's theorem is discussing about voltage sources, whereas Norton's theorem talks about the current source. Then we try to understand the statement of Norton's theorem and its explanation, and then move on to solving problems. Norton's theorem. The statement of the theorem remains the same. You can just observe any two-terminal linear active bilateral network. So there also I have used the same three words, linear active bilateral. Here also I am using linear active bilateral network. There any two-terminal linear active bilateral network was replaced by a single voltage source in series with a single resistance or impedance. Here it can be replaced by an equivalent circuit consisting of a current source, which we call it as I Norton, in parallel with a resistance R Thevenin or R Norton. R Thevenin and R Norton are one and the same. Like how we do it in our source transformation, voltage source to current source, if you do it, voltage source value will be converted into the current value, but series resistance will become a parallel resistance in case of current source. Similarly here also, the value of this resistance doesn't change. So whether you solve it for Thevenin's theorem or Norton's theorem, the calculation of this value remains the same. It's not going to vary. Only thing that is going to change is the circuit representation, whereas in that case you are connecting a current source in parallel with a resistance in case of Norton's theorem, where I Norton is a short circuit current between the terminals between the terminals, that means between the open circuited terminals, and R Thevenin is the equivalent resistance measured between the terminals of the network with all the independent sources replaced by its internal resistances or impedance. The statement remains the same. It's not going to change. Only change that we have come across here is the representation of the circuit in case of Norton's theorem is with the current source. In case of Thevenin's theorem, it is with voltage source. Explanation. So, the same circuit I have considered here for better understanding. So, we need to find the current through the load resistance by applying Norton's theorem. The same circuit, it has voltage source V with resistors R1, R2, R3 having 2 loops, and you have to find out the current through the resistance RL by applying here Norton's theorem. So, for that what we have to do? Once again, remove the resistance RL from the circuit. That is what. Step 1 is to remove the load resistance from the circuit. Then we are not calculating open circuit voltage here. Instead, we are shorting those two terminals. Shorting those two terminals, okay, we are trying to find out the current through that. That current I am calling it as I short circuit or I Norton. That is the magnitude of the current source that we are going to replace. Okay. So, now remove RL from the circuit, short the terminals AB and find the short circuit current. This is I Norton. How to calculate that? Now, look at the circuit here. You find actually because of the source connected here, a current starts flowing here. That current at this junction, find two paths. One current flow through R2, the other current flow through R3. And again R3, there is no other path here, it flows through the short like this. Okay. So, that means since the current divides between these two paths, R2 and R3 are in parallel, that is in turn series with R1. So, find out the total current through the circuit by using the expression V divided by R1 plus the parallel combination of R2 and R3. Okay. So, you get the total current which is flowing through R1 here. Okay. That is the total current. That current, actually we need to find out the short circuit current here. We have found out the total current in order to find out the current that is flowing through the short circuit here. So, once we know this current, it is by applying current division rule, we can find out the current through the short. How to apply that? So, we already know that if a total current is entering a parallel branch consisting of two branches, then the current through one of the branches is nothing but equal to the current, the total current multiplied with, for example, if I have to find out the current through the resistance R2, then current, the total current multiplied with the resistance of the other branch. The resistance of the other branch in this case is R3 divided by R2 plus R3 in case if I have to find out the current through R2. But since we have to find out the current flowing through the short, that is nothing but the current which is flowing through R3, we have use the expression current division rule once again. It is total current multiplied with the resistance of the other branch is R2 divided by sum of the resistances R2 and R3, which is R2 plus R3. This is how we are going to find out the Norton's equivalent current. That is the magnitude of the current source which we are going to replace in this case. Next, equivalent resistance is same for both Thevenin's and Norton's theorem, as I have already mentioned. Equivalent resistance or impedance, it is the same for both the theorems here. So, I have repeated this for the better understanding. This step is repeated here for better understanding. Once again, short circuit the voltage source or open circuit the current source, replace them by their internal resistances. Find equivalent resistance by looking into the circuit from open circuited terminal. This is R Thevenin. This part I have already explained. Next, the last step is to replace the given circuit by its equivalent, the Norton equivalent. So, the Norton equivalent is a current source in parallel with the Norton equivalent resistance or Thevenin equivalent resistance, which are one and the same. To this, you have to connect the load resistance. Now, once again, you find two resistors connected in parallel. To this, a total current of I Norton is connected. So, To find out the current through RL, you have to apply current division rule. By applying current division rule, you have to find out the current through RL. So what it is? Once again, the total current, which is I Norton, multiplied with the resistance of the opposite branch, in this case is R Thevenin, divided by sum of the resistances RL plus R Thevenin. This is in brief how exactly we can apply Norton's theorem to solve any electric circuit. So then let us start understanding how to solve the problems by applying Thevenin's theorem. So we have already discussed a similar kind of problem, so it is easy for us to analyze this problem very clearly. The first question or the first problem here, using Thevenin's theorem, find the current through 2 ohm resistor. So in the circuit here we have 50 volts source connected to 5 ohms, 20 ohms, 4 ohms resistors, and the load resistance here is 2 ohms. Load resistance is 2. You have the circuit like this. What is the first step? As I have already mentioned in my example, it is you have to remove the resistance R from the circuit. So when you remove this 2 ohm resistor from the circuit, you find an open circuit, find out the open circuit voltage. So it's simple. It is you have to find out the current through this. The current through this is nothing but equal to 50 volts divided by sum of the resistances here, because it's a single loop circuit. So 50 divided by 5 plus 20, which is 25. So 50 divided by 25 is 2 amperes. 2 amperes multiplied with 20 ohms is the voltage here, which is 40 volts. So it is first removing R, that is 2 ohms, and we also have found out the Thevenin's equivalent voltage here. Next, the second step is to find the Thevenin's equivalent resistance. So to find Thevenin's equivalent resistance, you have to look into the circuit from the output terminals, the same thing. So instead of solving it from left side, you are solving it from the right side. You can just observe that it is 5, 20 and 4 ohms resistors are there. Once again, you just try analyzing this way. When you send a current through 4 ohm resistor, at this point it finds two paths, one through 5 ohm, the other one through 20 ohm, so that you can immediately say that 20 and 5 are in parallel, that is 20 ohm resistor and 5 ohm resistor are in parallel, together they are in series with 5 ohm resistor. So that R Thevenin is equal to 5 ohms in parallel with 20 ohms plus 4 ohms. So totally it is 8 ohms. If you simplify and find out the answer, it is equal to 8 ohms there. Then the Thevenin's equivalent circuit, voltage source in series with a simple series resistance of 8 ohms and 40, to that you are connecting 2 ohms resistor. So that current here will be equal to 4 amperes. So this is the first example we have. Next we will go to the second, wherein we have dependent source. So that is without any dependent source. Here we try understanding the circuit with dependent source. So for that, let me discuss it with the circuit written here. The same circuit plus minus the same circuit here, which is 20 volts, and you have a resistance of 6 ohms connected, and you have a dependent source which is nothing but a current controlled voltage source, and it is represented as 2I, and then you have a 6 ohm resistor connected to the circuit here, and I is nothing but the current that is flowing through 6 ohms. That means this dependent source is dependent on the current I that is flowing through 6 ohm resistor. Then you have 10 ohms, and this is the circuit. So you can just observe here, this is the circuit I am having, 20 volt source and 6 ohm resistor, a dependent source, a 6 ohm resistor connected once again here. The current through 6 ohm resistor is, the dependent source is dependent on the current which is flowing through 6 ohm resistor. So for such circuit, how to find out the Thevenin equivalent circuit? That is, you have to just find out the Thevenin equivalent circuit here. That means you have to find out Thevenin equivalent voltage and the Thevenin equivalent impedance for this. So for that, first write KVL for this. So if I apply KVL for this, so as we know, the current flows from higher potential to lower potential, so that the point here is plus and this is minus, once again here plus and minus, and the value of this resistor here is 10 ohms. Okay. The current, once again, since A and B are open circuited, no current flows through this. So the drop across this resistance is nothing but equal to VAB. VAB or VOC or VThevenin, all of them are nothing but equal to the drop across 6 ohm resistor. That is 6 multiplied with the current that is flowing through that. So for that, applying KVL to the network, if we start writing, it is 20 volts is an independent source and we are moving from negative to the positive end, which is a potential rise, so that it is with plus. Then the current flows from higher potential to lower potential for 6 ohm resistor, which is a drop if you move from higher potential to lower potential, so that it is minus 6 into I, and this is a source. We are again moving from minus to plus. Since we are moving from minus to plus, this is going to become plus 2I, which is a source, and again for the resistance, the we are moving from plus to minus, that is higher potential to lower potential, which is a drop. Once again it is going to become minus 6I, which is equal to 0. Okay. So that I can write the equation 20, which is equal to minus 6 plus 2, so that it is equal to 20 is equal to 10I, minus 6 minus 12, and then it is 10I, or I is equal to 20 by 10, which is equal to 2 ampere. Now we can find out VOC, which is equal to 6 into I, or it is 6 into 2 amperes, which is equal to 12 volts. It's equal to 12 volts. Now, so this is equal to 12 volts. So once again I repeat this particular part. It is by applying KVL, we are writing the equation 20 minus 6I plus 2I minus 6I equal to 0. So simplifying that, I am getting 20 is equal to 10 into I, so that your VOC or VThevenin is equal to 12 volts. So next step is, so now the other part of the problem, we'll solve it tomorrow. Thank you so much.